Hello, and thank you for joining today's webinar, 6 Degrees of Freedom, Optical Measurement for Biomedical and Biomechanics. My name is Jack Irwin, and I'll be moderating today's event. I'm joined today by some experts in the field of non-contact measurements for medical product development. First, we will have our technical product expert, Justin Paszynski, present on the ARAMIS optical strain gauge system and discuss its applications in the world of biomechanics. And we'll have two student presenters from the University of Denver, Sean Chen and Jack Yang, to talk about their work in micromotion and FEA validation. Finally, we will have our applications engineer, Andy Leonard, demonstrate the ARAMIS software on a spinal application. We will have a Q&A session after each presenter group, so please ask your questions in the Q&A section below, and we'll do our best to answer them. So now, without further ado, I'll pass things off to Justin to begin.
Thank you very much, Jack. Appreciate that. All right. Well, hello and welcome to today's presentation on 6 Degrees of Freedom, Optical Measurements. Thank you for your time and consideration today. My name is Justin, and I'm an account manager for Trilion Quality Systems. I've got a nice tan photo of myself up there. I thought I'd put a picture up of myself to make it a little more personal. As a young man, my father taught me that while working on various cars in our garage, that having the right tool for the job made all the difference in the world. And he'd often tell me, you're only as good as the tools that you use. And so fortunately, technology continues to make strides, and today's tools better meet the needs of testing than yesterday's tools. And so I'm here to discuss biomedical applications, next generation measurement, optical measurement, specifically 3D digital image correlation, 3D DIC. Maybe you've heard about this method or you've seen some of those colorful measurement series, but it's much more than just pretty pictures. So today I'd like to provide a brief overview of this new tool and how the advantages far outweigh other methodologies with consideration for the biomedical industry. I work for Trilion Quality Systems, an American engineering firm. It's been in business for the last 20 years, specialized in the development of optical 3D measurement and analysis tools. And we help our customers with application development, consulting services, and turnkey system deployment. 3D DIC has been around since the 80s and was productized in the 2000s as camera and computer capability reached new highs. Recently, our new fixed base and automated kiosk systems have been a catalyst for the industrialization of the technology. So it's not just for the PhDs anymore. We're a growing business with our headquarters in Philadelphia and offices throughout the U.S. Each office keeps systems on hand and supports businesses locally visiting for service work and for training. Trilion is the exclusive North American testing distributor for GOM. GOM develops the software and the industrial systems for 3D coordinate measurement and 3D testing technology. GOM is recognized worldwide and has over 16,000 system installations to their credit. So here's the GOM lineup of measuring systems, and I think it's important for us to understand these before we move forward. There's the ARAMIS. It's our most robust tool. It is indispensable when monitoring and analyzing the development of displacement or strain fields in time. Moving forward, I'll be presenting primarily on this topic. There's also the ARGUS, the static forming analysis tool that yields full field strain, thickness of material, and it replaces circle grid analysis. There's TriTop, a mobile coordinate measuring machine, bringing the machine to the part. It's great for large specimens and static deformation. There's the GOM CT. This is a 3D X-ray. And for the first time with GOM, we can see beneath the surface and gain insight into our designs. There's also the ATOS, the 3D scanning tool, good for reverse engineering, shape and tolerance. And all these solutions work together. Projects can be shared from software to software, and Trilion offers services to visit you and perform a measurement. Let's take a little closer look at the CT before we move on. I'm just going to click this here, and we're going to go into CT for a moment. With CT technology, we can evaluate both internal and external geometries in really fine detail. So take a look at this GOM pen. You can evaluate material defects like cracks and other damage, failure. You can look at porosity and slag inclusion. You can even examine wall strength of a given material. Perhaps you're considering quality checks like the shape and dimensional checks that for tolerancing your design, or you could be conducting a non-destructive reverse engineering of maybe a rival product like this mighty GOM pen right here. It's a really nice dense surface mesh It's really powerful looking data here. The CT gives full field non-contact 360-degree volumetric measurement. That's a mouthful. There's really no standard application here for this precise non-destructive inspection. And I think that for certain industries, this is really important. Quality control, additive manufacturing, injection molding, tool correction, and especially with relevance for today, medical components. It's a 225 kilovolt 3D X-ray that can handle specimens up to 400 millimeters. And here you can see that small footprint that the CT carries and the workstation that's right next to it that controls the CT. Because the hardware and the software are developed together, you can conduct an analysis in real time right on that workstation. The GOM CT offers industry-leading resolution, and you can see here it's identified a feature at 1.5 microns. It's found to be the most accurate by third party, comparing us to other industry leaders. They found that we are the most accurate in our 225 kilovolt space. And we are found also to be easy to use. We have a 5-axis position process that speeds up your scan. It speeds up the scan so much that here we have a complete X-ray imaging for a full surface mesh in just under 5 minutes. So really powerful. And if you have an interest in learning more about the GOM CT metrology tool, its capabilities or its limitations, please reach out for some answers. I thought I might share that. For now, let's discuss 3D DIC by investigating the 3D deformation analysis tool ARAMIS. It's essentially an optical strain gauge for full field strain and displacement measurements, and includes hardware and software designed together. And it's comprised of a pair of cameras and a light. ARAMIS uses a principle of triangulation, photogrammetry to measure 3D coordinates along the surface. It does this dynamically, so it sees just like your eyes see in 3D. The software gets just acts like your brain and puts the left and the right images together, puts them together into a triangular 3D mesh. So we use a regular or a random pattern that has really good contrast, and we apply that to the surface of the test object. And when that pattern moves and deforms, it will deform along with the object. That's the main input for the algorithm to track movement, expansion, or compression of the material's surface. So here you can see a test with a person running up to 10 kilometers per hour. And we're capturing it 200 frames per second. This is a really narrow structure, and it has just small, lightweight adhesive dots. These are target dots. And we can measure the bending or stiffness of the prosthesis by placing these dots down. And so this is a relative displacement measurement with the dots along the blade measuring against target dots on the knee. You'd have to look pretty closely. Hopefully you've got your monitor, a really large monitor, or you're up close. If you see on the knee there, you can identify some target dots. We select these in the software and use them as reference, and so that we can do a rigid body motion correction and essentially take out the global motion and isolate the bending of that blade. So this is a pretty precise 3D displacement measurement. And anywhere you put a sticker, you get a 3D coordinate for point tracking in the time domain. So in that way, we're able to get 3D velocities, 3D accelerations, and 6 degrees of freedom, all just from these adhesive dots. We also can take a look at speckle patterning. So ARAMIS can use pattern on surfaces to create thousands of tiny dots that the software will divide up into nodes for tracking. And from these nodes, a strain map can be measured on the whole of the surface. And this is just off-the-shelf aerosol paint, sprayed flat white and speckled flat black, and the software automatically identifies and tracks the high contrast of the pattern. So these nodes, they each kind of look like a QR code with the speckle pattern, and they can be inspected for their displacement in X, Y, and Z, but they can also be inspected for their relative motion to each other. And so effectively, they contain strain information. So you see this complex strain field on the right here. This is a yielding effect that's really common in composite structures, but you can also see it in a lot of different metal specimens. You just don't see it with traditional clip gauges or strain gauges. So what you get from 3D DIC from the results are 3D shape of the component, you get 3D displacements, you get the 6 degrees of freedom, and the 3D directional strains. So you can see with all these results, this is very useful in biological specimens during in vitro or in vivo style testing that can get pretty complex. So typically labs use instrumentation like LVDTs, extensometers, accelerometers, foil strain gauges. These are all contact sensors at single points, many of which collect a lot of data, uh, maybe a few thousand times per second. So they give you 1,000 values at one location, just a single location. Possibly by placing this on the surface, you could disturb the local mechanical response of the material. This is especially true for soft tissues within biomedical. And you're really only getting this discrete location of data, not the global strain information. And you're going to suffer from longer setup times. You're going to have lots of wires. And one critical nuance here is that in biomechanical testing, it's really hard to predict non-homogeneous and anisotropic materials, especially with complex geometry. ARAMIS 3D DIC acquires a single value at 1,000 locations. It's non-contact. It collects in full field. We say full field a lot, but look at this holistic measurement. So you can inspect strain gradients and concentrations. And we provide not just the global, but we give you the local as well. You can click a point in the data set to inspect a discrete location if you'd like. So anywhere you click, you're going to get that data point. It's very ergonomic, it's self-contained, it's not wires everywhere. And what's really interesting is after you collect the raw images, you can define points of interest at the end of the test. So you're retroactively inspecting the data and placing virtual strain gauges, virtual extensometers down. And so on the right here, we've got the finite element modeling and analysis. This is a really powerful numerical simulation tool. The ARAMIS is a nice bridge between the FEA and the testing lab. It gives them a testing tool that captures the full 3D coordinates of surface of the part under load and provides thousands of points for comparison to models. This helps the simulation engineer get simulations as close to reality as possible. I think even Dr. Fauci would recognize that simulations are only as good as their assumptions. But that said, it's important for us to consider the optical technique in its accuracy and precision. So as a point of comparison, ARAMIS 3D DIC is certified for displacements as a Class A extensometer following ASTM standards. And then also the ARAMIS 3D optical strain is it's less precise than a strain gauge, but is much more accurate. So it has a noise floor of 50 to 100 microstrain, but it's been shown through third-party testing to be within 10 microstrain of the actual value over multiple identical experiments. So ARAMIS 3D DIC has a sensitivity of 1/100th of a pixel, amounting to, according to this grid, you can kind of see the displacement sensitivity here, to 60 microns at 5 meters, and we become submicron sensitivity at 100 millimeters, and we go even lower as our field of view grows lower. So we've mapped out the strain gauge length and the sensitivity for our fixed systems here. It's all thought of for you at this point, and it's really designed for ease of use. A lot of progress has been made in the world of mechanical and material engineering with regard to ARAMIS. It's been certified by NIST, and it's been recognized as equivalent to standard testing tools by Boeing and used in their FAA testing. But it has huge potential in biomedical specific materials. It's non-contact, so you can avoid deforming materials and deformable materials like you often encounter. You're going to get full field results, so having the full characterization of biological tissues, organs, biomedical devices is really important. This helps with bone remodeling, bone fracture, anything with features that are inhomogeneous or anisotropic, and it's useful for identification of crack initiation or crack propagation. You need to have full field to do this stuff. 3D displacement and strain fields at the same time. This gives you the 6 degrees of freedom, which is really perfect for spine and prosthesis testing. We're really flexible, so we can move from micro to large scales. I mean, a 10 millimeter field of view to several meters field of view. And having a single tool for any size coupon, this is really useful for soft tissues that vary in size. And just by changing the lenses, you can change your field of view. We're material independent, so we can move from implants to bones and to human skin. We're going to see that later. And we can move from static to high speed. That means we can do before and after. A good example of this might be an implant placement, for instance, or we could go dynamic with impact testing, inspect hammer strike location or bone saw motion for orthopedics. We also have this integrated massless vibration analysis where you could monitor structural integrity of a bone. And with our FEA validation workflow, you can get your simulations closer to reality than ever before with just a single test iteration. So you can see some notable testing that we do across industries here. Automotive crash testing, structural motion analysis of design. In civil engineering, we do destructive testing of beams. We do structural health monitoring. In aerospace, we see the replacement of strain gauges along the wing of a plane. And we do a lot of destructive blade out testing in this space as well. Within consumer goods, we work with everyone from electronics to clothing lines. And, find us at your local university because chances are they've heard of us. And so today, I'd like to concentrate on a few case studies in the biomechanics realm and to more clearly understand the technology. So let's look at material testing first. So we have 8 different input channels that allow you to bring in the load and synchronize your data. And so we can get some dimensional information and calculate stress strain curves, and we can follow ISO ASTM standards. And this type of setup is perfect for use with servo hydraulic machines or electric models, plenty of different load frames, or even in vivo applications, as we'll see. And so looking at the automated material testing with ARAMIS, we can be used as a video extensometer to replace traditional extensometers. But the full field strain results contain much more information than just your typical video extensometer or even just a regular extensometer, because it gives us the local plastic strain where the necking occurs. And that's just something that's not picked up by conventional tools. Here we've got the stress strain curve and the material data, and they're calculated for us according to common ASTM and ISO standards. And you can see the poisons and the modulus value automatically calculated with it along that curve. With the study of different plastic deformations, it's crucial to understand where the necking occurs, and this is a profile that points that necking area out perfectly for us. Remember, we're capturing in 3D, so we capture shape. The software has an automated flatness map that reveals how flat the specimen is aligned in your load frame. It's capable of showing the thickness reduction during the necking, and a lot of times we see it, and we know you guys do too. People are measuring what they think they're measuring. Having your specimen loaded in correctly within the groups or having a load that's asymmetrical can result in some funny data. So we're really powerful in material testing. So I'd like to move on and show you some really cool stuff within the biomedical world. I've got a few applications to show you to focus it a little bit more here. So using ARAMIS 3D, you can examine in vitro localized Achilles tendon strain. This is not a uniform strain to a common load here. There's a greater strain within the dorsal region, not the ventral portion. It's more frequently injured. You can see that strain build up at the very top here and then break at the bottom. It's really interesting to see the way that strain propagates towards the bottom right before rupture. It's an industry that's probably making everyone kind of cringe right now. You can almost feel it, and there's usually an audible pop sound when it occurs. And if you've ever had this happen to you, well, maybe that's hitting home. We first developed some skin measurement on hands, and we found that it works really, really well. As you can see here, we've got some pattern on the palms of our hands and just moving it around. You can see even the strain flow in the right image there. We later worked with the University of Pennsylvania Medicine on a study of Botox and the reduction of facial wrinkles. And well, I guess you'll have to read their white paper to understand the findings that they have. But we ended up using clown paint for those face patterns, and it worked really well. And so now we have skin studies that are performed regularly by customers like L'Oreal, Estee Lauder, and they've become really good at making measurement for anti-aging serums. You can see here the flow of major strain across the subject's face as she goes from resting to smiling. Yeah, pretty cool. Nice looking pattern there too. Our customer support representative, Sophia, allowed us to feed her some sugar cookies. I don't know how you say no to sugar cookies, but they were known to make her baby kick. And so we can make a good out-of-plane measurement of her baby kicking just after she eats these cookies while the baby's in utero there. Pretty cool looking data set. You might notice in the very far left image there's a bit of glare on her tummy there and the loss of data. This points out that we have to be able to see it to measure it. And certainly we've got some other pregnancy videos to show too, but I thought this one was pretty nice. So I'd like to go into a surgical technique, the Latarjet surgery. A Latarjet procedure is performed for patients who have shoulder instability. Their shoulder pops out of the socket, the glenoid. It can be damaged by dislocating it over and over, and then you get a bone loss and a portion of that glenoid. And so what ends up happening is the surgeon will end up cutting a piece of the shoulder and replacing it there on the glenoid, grafting it on there. You can see it grafted in the image on the right. It's actually screwed in, and it's to make it more rigid, to stop it from popping out. And so there are different techniques or methods for fixing that segment of bone onto the glenoid. You can see a couple here. And the procedure is meant to make the shoulder have that improved stiffness. So, well, they need to consider what fixing method is the best and which one will have the least amount of deformation into the bone segment and the connecting shoulder blade. It's not trivial. So the methods we will show use 2 screws, and it's an actual specimen you can see at the bottom here, the bottom square. It's made of artificial bone material, which closely resembles human bone. So first we scanned the individual components of the test so that we captured the full shape of the parts. And we're able to conduct motion analysis of areas that ARAMIS cannot see when you do this. But here we're just using the mesh to create a nice visual for our results. We'll be inspecting the motion analysis and rotation of the bone graft transfer procedure and examining that the fixation technique and looking for hotspot areas of high deformation along this. So you can see a nice visual there. But here's the video. So we use target dots on the screws for displacement information and speckle patterning on the bone for strain analysis. This is a cyclic loading of the bone segment with 2 screws until we have ultimate failure of the part. Here you can see a nice overview of our test setup and its analogous human representation. Let's take a closer look to see our constructed inspections in this next slide here. So you might have noticed we had target dots in the video. They were all around the bone segment, and they show up as pink dots here. They're identified as the software automatically. The dots were placed here for reference for our rigid body motion correction. It's a motion compensation that's done in our software to quickly select a group of rigid target dots and compensate for the 3D displacements of the group dynamically throughout the test. So in this way, we can isolate the movement of the fixture and look at the motion of each screw and even inspect the yellow dots, which are the dots laid on the punch or the humerus bone as it cyclically loads. So let's look at some results. Here we have major strain analysis, which shows concentration of strain near the top screw before it fails. There it goes. I'll play one more time here. We can drop down a couple of points just by selecting along the surface there, and the software will automatically diagram the data across the project for us. We see clearly point 2, which is the green line on the top of the graph. It's experiencing higher strain levels, maybe 0.5% more strain during that peak load. Also, you can notice the load brought in at the bottom graph here and synchronized together with our data. So you inspect these color maps. It's an easy way. It's as easy as clicking anywhere on the speckle pattern wherever you want to get information. The software can automatically find the max strain area for a strain distribution. Another way our software can visualize the results is to look at the major strain direction arrows that allow us to see the flow of strain. This is really, really cool. You can see the compressive deformation where we have the punch transforming the load onto the bone segment. And then on the other side, the opposite side of the bone, where the failure occurs, we can watch the flow build up and concentrate right there during the progress of our test. Next, we have the motion analysis of the two screws. The target dots on the screws enable us to look at the 6 degrees of freedom for each screw. So here we are examining the rotations. This is in the Z direction, so that's towards the screen. Let's take a look at the comparison between these screws. So looking to our diagram on the right, the top screw is shown in the black line, and it experiences a lower level of rotation. But the blue line at the top is representative of the bottom screw. So you can see that it experiences a higher level of rotation. So this is in the, remember this is in the Z direction, so that slight upward trend that you can see in the blue line is the screw loosening itself. And this was actually interpreted as the bottom screw loosening and the top screw tightening because the screws rotate in opposite directions. And so this is a very unique measurement and a very powerful ARAMIS tool. Next, I'd like to jump to a motion analysis on the MMCL ligament. I hope you guys aren't too squeamish as we dive a little deeper into ligament tissues and another in vitro setup here. The purpose of the study was to investigate the influence of the ligament on the stability of the AC joint. It's basically just the top of your shoulder. So specifically, we're going to look at the motions to see what resistance the ligament offers. If you look closely, you can see our target dots are applied here. The software automatically finds these dots, and we separate them into different components for evaluation. Each dot is a 3D coordinate for displacement tracking. So you can see the black dots are representative of the MMCL ligament, and the red dots at the bottom of the fixture are used as reference for our rigid body motion correction. Once again, we're using one of these. And so here's the video during the test. It's really slight movement, and we have a vertical translation from that actuator. And this is inducing the load and gives you a subsequent motion into our AC joint. So there's things here that the naked eye is not catching. Let's take a look. Here's a typical resultant data analysis from one of our projects. Okay, you get 3D vectors showing direction and magnitude, and because we have target dots throughout, we get a holistic measurement that's really intuitive to see. So with regard to the magnitude here, these are really small displacements from 100 to upwards to 800 microns, but certainly some of these points are very, very small, and we're able to see that. So we can select some of the points to plot in our diagram for inspection and look at the differences between the displacements that are happening on the different parts of the AC joint. So this test was carried out a little bit further than what we're seeing here. First, they cut the trapezoid and the conoid ligaments, and the test was repeated to understand what would happen if there was only MMCL ligament left, and how does it react to the vertical load of the AC joint. But we've spared you the cutting of those tissues here. We just wanted to show you how we can be used in an in vitro type of situation to view these parts holistically, but also to isolate regions, conduct comparisons, and you can select discrete locations and plot the data. So the femur and temporal bone of the skull and are the strongest bones of the human body, but the tooth enamel is the hardest substance, and it makes it the hardest bone in your body, really. It's really highly mineralized. But life is hard, and candy is really, really good, and so many people experience the loss of a tooth, and that the implant replaces the tooth's root and carries the artificial crown. If you've if you've ever had this happen to you, the word crown can just send shivers down your spine. With our technology, we can digitize the dental imprint as a 3D surface data for the production of that crown. You can take a look at the bottom right there of that dense surface mesh that can resemble your tooth as best as possible. When considering the implant in the crown, there's a long-term durability that needs to be considered. There are some implants inserted into the mandible here. And here's our test setup. So we have a test rig with a mandible and our two crowns that are loaded by means of two different pistons there. And we pattern our surface and the two crowns with a speckle pattern to derive a strain analysis on these areas with ARAMIS optical strain. Nice looking pattern there. The result gives a clear image of the strain and deformations occurring. We have compressive deformations directly underneath the crowns where the implants are interacting with the mandible. and we've got strain deformation on the neighboring area on the mandible. The actuator is actually just mimicking a chewing force, but the ARAMIS optical strain measures the low straining effect along that mandible. And so again, it's really intuitive to look at to see what's occurring here. The next example is related to the optimization of simulation, and it'll be my final example. We've got some notable customers in Johns Hopkins and Mayo Clinic who use ARAMIS optical strain for the validation of their numerical simulations. They find that ARAMIS enhances the validation of their models. And so here the ARAMIS optical strain is used to measure the strain distribution of a hip implant. The test setup is on the right there, and the machine transfers the load onto the sphere of the hip, and the strain levels are measured on the shaft. You can see the speckle pattern is applied there. And so you can see the simulation in the top image and the reality result from ARAMIS in the bottom. And this shows a really good correlation. The inspection is in the direction of compression, and the views here on the right are with the sphere at the very top. Nice looking data. So we often hear from customers, can I compare my measurement against simulations? They often just want a nice picture in the software, maybe as a report page, a side-by-side comparison, and they say that this would be a really big thing to them. And certainly we can do this, absolutely. So unfortunately, I don't have any, most of the things I have are proprietary, so I'm going to show you here just a nice looking comparison we've done on a wrench. And so ARAMIS gives that full field data, and so it meets this requirement that you need to compare with FEA. So you can notice the slippage on the wrench here, and this is a clear case of a boundary condition error that occurs in testing. And it's a real reason why adjustable wrenches are a lot more effective, in my opinion. But in general, the ARAMIS system results are great to compare to simulation. The data is very, very similar, so we have 3D meshes in both software worlds. And ARAMIS software allows for the export of the mesh to your software. We can export in formats like STL, UFF, IGS, but as you can see on this slide, we can import FEA too. So we work with all the major softwares, ANSYS, Abacus, LS-DYNA, and we can build those differences. We can make even further evaluations, so you can see the widening of the wrench here. You know, ARAMIS allows you to conduct a data alignment, and so you can create a map, a deviation map, as you can see in the bottom right corner. We've got lots of experience with aligning CAD and CT data, so aligning FEA is really, really easy in ARAMIS. So once you're aligned, you can create this nice deviation map and see those differences. This is a real surefire way to speed up any validation process that you might have. So ARAMIS is powerful for biomechanics. It's the next tool for the biomechanic researcher, and it provides full field 3D deformation, true strain results from applied loads, just not possible with conventional methods. The complexities of biomechanics samples are so great that the theoretical models are difficult to realize. So with proper experimental results such as this that I've shown you, you can get better material properties, you can understand local effects better, and you can get better resultant models verified. There are many, many different tests performed with our products and driven by you as our customer. Your standard is our standard. So please reach out to us if you'd like to know more, to more critically understand this technology related to your own applications. And please go download the free software at gom-correlate.com. You can begin with 2D measurement and have access to the 3D sample files. And the bigger message here is you can begin utilizing the right tool for the job. So thank you very much.
Thank you very much, Justin. That was excellent. Over the course of your presentation, we did have some questions that came in. We're going to answer those now. We're going to take the time to go through some of those questions. If you had any that come up, now is a good time to ask them to Justin in the Q&A section that's at the bottom of your screen. So the very first question comes from Mensa Venkata. He asks, can we measure strain on a tubular specimen during tensile testing?
Yeah, absolutely. We often are looking at interesting geometries, and so I guess the only point of limitation there is that within our measurement, the left and right cameras both have to see it. So we'll be able to capture half of that tube, and if you wanted to see the back side, then we would either use a second system to try and give you as close to 360-degree coverage as possible, or we could quite possibly use a mirror. And oftentimes we end up using mirrors because we can capture the backside as well as the front side all in one shot. And so having these types of unique geometries is the name of the game here. We're capturing the shape. It's not a problem for us.
Great, okay. We'll move on to the next question then. This one comes from James Bishop. Try to get this right. In the prosthetic leg, would we need to define the entire set of point targets to be included in the definition of the rigid body? Meaning within the software, Justin, do you set that up, the rigid component as opposed to the deforming component, either before the test happens or in post-processing?
Yeah, actually, you can alternate what you'd like to set to be your rigid body. You can even transform it upon itself if you'd like. It's a really quick function in the software where it's just a drop-down box. Essentially, after you create all your different sections of dots that are different components for the test, you can then make anything in the field of view, any one of these components in relation to another, and you can isolate them one by one like this, turning them on and off. And so it's not really a difficulty to do it in the software at any point in time. I guess you just want to, ahead of time, put dots in places that you think that would be useful for you with regard to a rigid body. Hopefully that answers the question.
Excellent. Yeah, I think that was a good answer for that. Moving on to Justin Hertzler. He asks, curious about the requirements to attach dots to soft tissues for analysis. Meaning, you mentioned some of those target dots before being made, out of an adhesive subject or, paper even. How has that worked in the past for, cadaver tissue, things along those lines?
So we've got a lot of experience in the game. We've been around for 20 years, and there's a lot of people that are higher experts at this than I am. But sometimes we can use dots, no problem. But other times we want to spray on a pattern. Maybe we want to use a powder to lay down maybe a graphite powder onto the soft tissue. It just depends on the application. It depends on the tissue. And we can help you solve these problems. We've got a lot of expertise to do that. And we've been down these roads with customers before. So please, I think that there should be a follow-up question to this. And the follow-up question would be, what's your application? What's this issue? And how can we help you to solve that issue?
Great, okay. Next one is from Philip Chu. He asks, for the motion analysis, are those ligaments being used for the test real? Were those cadaver ligaments, Justin?
Yes, they were. They were real ligaments, yep. And the keys, with the Achilles tendon as well, these are all cadaver portions that were in vitro. We've done some in vivo testing as well. I just didn't include that here. Maybe next time. There's plenty of projects we've done in the past. So, but yeah, those are absolutely real.
Great. Okay. Okay. Another question from Metza Venkata. Can we measure strain on a component of 0.06 millimeter width? An example of this would be a coronary stent expansion. How does the technology work on specimens so small?
So I will say that it becomes difficult to get a strain measurement on really small components. You give us the width here, but I guess what would be important would be the surface in which we're making the measurement of strain. And so if it's really small, we're going to have to get our field of view as small as possible to be able to capture that. But 0.06 millimeter is quite small, so I guess maybe it might be best for us to take a look at what we could see for you. I think I'll just leave it at that.
Okay, fair enough. I'll mention in my experience as well that, on a similar technology side, still utilizing the DIC technique, we've had experiences down to, several hundred microns in size and been able to be successful with that. So we can follow up with you after the presentation, Meta, and answer your question further from there. All right, next is from Pradip Acharya. Can I measure the displacement or stress distribution between the meeting of two teeth during a bite analysis?
Yeah, so we've done some work in this area where we can look at strain and displacement distribution. We're always calculating stress, never actually measuring stress. But if we're looking between two teeth, I would assume we'd be looking at an implant, or we'd be maybe looking at some sort of a tray, a dental tray perhaps. And absolutely, we could look at the individual teeth, and as they clench down, we could see that propagation across the two.
Great. All right. Moving on to Jingji Hu. Can we measure strain distribution on soft tissue, such as skin? Would DIC be possible for strain map measurements of soft tissue immersed in a physiological solution?
Yeah, so the first part of your question is yes, we absolutely can. We do have some projects I'd love to show to you where we've done some soft tissue strain distribution that I could absolutely prove that to you right off the bat. But the strain in the solution, we would have to come up with a way to have the pattern remain in the solution, which may or may not be an issue, but we would need to look into that for you.
Great. All right. Moving on to the next question, Michael Goering. Did you state Class A extensometer? If so, how is it certified?
This is actually certified by a third party, and I actually have a nice project that I could share with you that goes through basically the certification process that was followed for the ARAMIS to be certified as a Class A. So I'd be more than happy to share that with you, Michael, and it'll go through that third-party study for you.
Okay, finally, one last question, move on to our next presenters. Do the pictures need to be taken by the GOM software and hardware, or would pictures from other cameras, are they capable of being analyzed by GOM?
So we like to say that we can use any images, we can pull in images, but when you have a 3D setup, as everything I showed you today was a 3D setup, and to get these cameras to synchronize together, to capture together, to be calibrated together, the GOM software and hardware is integrated and works perfectly for us. It's designed for this, so these measurements are designed for GOM software and hardware. It's all set up as a full turnkey system. We do use third-party cameras, high speed situations. We, Trilion, thinks together the cameras. We've developed a way to synchronize cameras and get them, export out the images and bring it into the software. So it is possible, but it's we're always using GOM software, and we're often using Trilion's expertise to get two cameras to work together. Hopefully that answers you as best as possible there.
Excellent. All right. I think that should do it for this round of questions. At this point, we're going to move on to our next round of presenters. We have two students from the University of Denver, Jack Yang and Sean Chen. We're going to be presenting on some of their applications where they've used the ARAMIS equipment. First, we have Jack Yang, who will be presenting a validation of a finite element model of cementless tibial implant for micromotion. I'll go ahead and let Jack take over from here.
Hello everyone, I'm Jack, PhD candidate from University of Denver. My topic today is validation of model predicted proximal tibia displacement and tree micromotion in cementless total knee arthroplasty. Initial fixation of cementless tibial trace after total knee arthroplasty is crucial to bone ingrowth. However, macromotions at the tree bone interface cannot be directly measured experimentally. Previous studies investigated interface macromotions through finite element methods but few performed validation on cadaveric specimens with physiological loading conditions. Hence, the objective of this study was to develop an experimental computational validation framework for predicting tibial micromotions and bone deformations during activities of daily living. 3 cadaveric tibia were implanted with cementless rotating platform, cruciate retaining tibial prosthesis, and potted into fixtures. Marker couples were placed at the exposed anterior surfaces of the tray and tibia. A speckle pattern was applied on the tibial surface to enable measuring surface displacements. The tray and tibia surfaces were also probed using the Optical Strain System to reproduce the same tray bone alignment for the later finite element models. The constructs were then mounted into the 6 degrees of freedom AMTI Vivo machine to simulate gait, deep knee bending, and stair descent. Experimental boundary conditions were derived from telemetric implant data and ASTM standard. After bedding in under cyclic compression, 40 cycles of each activity were performed. Relative displacements between tray bone marker couples and the proximal bone surface displacements were recorded using a DIC system. This is the animation, shows the DIC system simultaneously measured the marker and surface displacements. Finite element models of the tibia were developed in abacus from CT scans. Elastic properties of the tibial elements were assigned based on Hounsfield units using established relationships and calibrated with bone mineral density phantom. Implant alignments were reconstructed and calibrated by using surface models of the bone and tray obtained from DIC and Optical Strain System. The deformable bone implant constructs were loaded through a rigid femoral component with the output loading conditions from Vivo machine. Uncertainty bounds for the computational predictions were generated by perturbing tray alignment within experimental uncertainty and perturbing coefficient of friction. Experimentally measured and computationally predicted marker and bone surface displacements were compared to quantify the model performance. Here is the animation shows the computational model reproduced the gait experimental test. To quantify the correlation of measured and predicted surface displacement, the captured surface was divided into 5 regions. The average displacement within each region was calculated for every 1% of the activity cycle. The correlations between the prediction and measurement was then calculated and visualized by creating a scatter plot and applying linear regression with those 500 comparison pairs. Here are some results. Comparison of predicted and measured marker relative displacements for one specimen was showed here. The root mean square differences between the measurements and predictions from best matching simulations were less than 20 micron for all activities. Corresponding correlations were no less than 0.88. Graphic comparisons of tibial surface displacements at 30, 50, and 70% of the cycles for the same specimen were showed. The predictions correctly captured the activity unique experimental trends and closely matched the magnitudes. The average root mean square differences was 80 micron, which is about 10%, and the average correlation was 0.92. Good validation results were obtained for the other 2 specimens. So after the validations, the tree-bone interface micromotion contour maps were investigated computationally and compared with the predicted marker relative displacements. It was found that the marker relative displacements under-predicted the actual interface micromotions. This was mainly because that peak interface micromotions usually occurred in between the positioned marker couples. Even if all 9 marker couples were enabled, the under-predictions still exist. This study presented a validated experimental computational framework for investigating micromotions at the cementless tree-bone interface. Model predictions accurately matched both trend and magnitude of marker and bone surface displacements. The model distinguished between locations, activities, and specimens. The reliability of the validations was significantly improved by both considering marker and tibial surface displacements. Using marker relative displacements to assess the fixation performance could be a reasonable approach, but it would under-predict the actual interface micromotion. Thank you.
Very nice, Jack. Thank you so much. Now we're going to move on to our other student presenter, Sean. Sean today will be presenting the measurement of a femoral bone deformation after femoral plating to treat Vancouver type B fractures. And as Sean is pulling up his presentation, please remember if you have any questions for either of our student presenters today, feel free to ask them in the Q&A below at the bottom of your screen, and they'll both be available to answer those questions at the conclusion of this presentation.
Good afternoon, everyone. So today I'm presenting the measurement of femoral bone deformation after femoral plating to treat Vancouver type B fractures. So Vancouver type B paraprosthetic femoral fracture accounts for 70% of all PFF cases after total hip arthroplasty. And you can see the type B fracture is primarily characterized by the fracture around the femoral stem or just below the tip of the femoral stem. So a lateral implanted FCL plate screw construct has proven to promote healing of the primary type B PFFs. However, incidences of refracture at the distal screw were reported clinically, as shown in the picture on the right. There are limited insights on how the construct may affect femoral deformation and strain after the healing of the type B paraprosthetic fracture that could lead to the refracture. Therefore, the objective of this study is to develop and validate a finite element model of a commercially available fracture fixation construct for type B PFF using physiological femoral loading. So first, we take a look at the study overview. So we first developed an uniaxial loading configuration based on a gate loading finite element model. So the gate loading finite element model used musculoskeletal model calculated hip contact force and muscle forces as input, whereas the uniaxial loading configuration matched the femoral strain energy density of the gate loading model. And then we performed experimental validation using the femoral deformation of the model predicted results versus the experimental measured results for both the THA and the plate implanted cadaveric femurs. And using the validated THA and the plated femoral models against experimental measured femoral deformation, we further calculated some strain outputs using the FE models. So the CT of a fresh frozen cadaveric specimen was used to develop the FE model of the femur. And for the THA implanted femur, it included a commercially available THA femoral component. So the gate loading finite model was based on the input for the finite model was based on the peak hip contact force and femoral muscle forces during gait, which was calculated from a previously published musculoskeletal model. So the boundary conditions of the gate loading model is shown on the left, and the mean strain energy density values were calculated in 30 cross-sectional volumes in 10 millimeter intervals along the diaphysis of the femur. And this was described as the ACD profile of the finite model of the gate loading under the gate loading condition, whereas the uniaxial loading model was developed to match the ACD profile of the gate loading model. And here you can see we optimized the uniaxial magnitude of the uniaxial load as well as the femoral alignment so that the ACD profile of the uniaxial model matched the gate loading IP model. So using the developed uniaxial loading configurations, we set up this experimental testing where we tested two cataract femurs. So because this is a cataract study and to protect the bone and the specimen, we applied 2/3 magnitude of the 1800 Newton uniaxial force. And we had two tested configurations which include a THA alone, which is the cataract femur implanted with a THA femoral component alone, as well as a THA plus a diaphyseal construct, which actually simulated a healed type B paraprosthetic fracture. And then for the FE model, they were developed using the CTs of the same specimens, and the virtual implantation of the THA and DP and the diaphyseal plate was conducted and replicated the in situ position of those implants in the experimental study. And then the bony-Young's modulus was interpolated from the CT Hansel unit, while the stem bone and screw bone interfaces were modeled as fully bonded. So first we take a look at the experimental, comparison between the experimental results and the FE model. So here you can see a vector plot at the peak load during the experiment, as well as the FE. And the vector actually agrees very nicely in this case. So this is the mean values for the two tested conditions of the experiment as well as the FE model. And you can see they agree, at least in trend, where if we took the percentage error between the FE versus experiment, we found that the median error of the femoral deformation was negative 4.7% for the THA condition and 2.1% for the axial plate condition, which is pretty good in terms of the validation of the model. So after the validation, we took a look at the model simulation results, at the femoral principal strings, and you can see the diaphyseal plate model predicted higher strings around distal diaphyseal screws. And if we take a closer look at the cross-section of the screw segment, we can actually calculate the percentage change in terms of the principal strings. And the finding of this FE model is correlated with the clinically reported the refracture site for after the implantation of the diaphyseal plate. We also took a look at the strain energy density, and the results of the strain energy density agreed with the results of the principal strings. So in conclusion, as observed in the experiment, FE model successfully predicted the reduction of the femoral displacement after the implantation of the diaphyseal construct. The FE models also demonstrated elevated principal strain and strain energy density around the distal diaphyseal screws, which was indicative of increased risk of refracture. Well, we're conducting further studies to investigate the impact of the contact definitions at the bone screw and the bone stem interfaces. And the validated model can provide a preclinical platform for the virtual development of fixation construct to mitigate the risks of the secondary fracture. Here are my references, and thank you very much.
Excellent. Thank you so much, Sean. At this point, we're going to be moving on to the Q&A section for both Jack and Sean. We did have a question come in over the course of the presentation from Jack there. Jingji Hu had a question for Sean. It was, would you be interested in performing digital volume correlation in addition to digital image correlation to study strain distribution in 3D? What challenges would you anticipate there? So Sean, or Jack rather, would you like to answer that question?
Yeah, I would prefer to use DVC devices if we are doing some strain studies. But I think currently we do not have that device in our lab. So is that correct, Sean?
Right. So the volume correlation would be nice. But at this stage, I guess if you can actually capture the region of interest, depends on the question you're going after. I think that's still you can validate your FE models using the the DSC system.
Excellent. Okay. If you have any more questions for our presenters, feel free to ask them. At this point, since we're running a little bit low on time here, we're going to move on to our next presenter, Andy Leonard. He's an applications engineer at Trilion. He's going to be going through the ARAMIS software on a spinal application, spine vertebrae motion analysis. I will go ahead and pass things off to Andy in order to take a look at that. So Andy, would you mind sharing your screen?
Absolutely. Thanks, Jack. So I wanted to review the spine motion analysis project that's been done. And before we go ahead and jump in, I have some talking points just to kind of motivate our analysis. So at its core, this was a motion analysis test to study three-dimensional fracture motion. And if you look at the video on the right, we see a specimen mounted in a multi-axis load frame, which is going to allow for simulation of natural motion and load transfer. We took this test over the course of 140 seconds, capturing images at about 1.25 hertz. And so we used 93 stickers for point tracking. Everywhere we put down a sticker, we're getting a coordinate in 6 degrees of freedom. But we could use more. And we could also use speckle patterning for full surface tracking. And unfortunately, I'm not at liberty to share the relevant project, but I have done very similar tests before, and the speckle patterning turned out beautifully. Also, I just wanted to call back quick to a question that came up earlier as to whether we put these stickers directly on the tissue or other means. And as you can notice here, we're using a variety of different methods. We are using dots on the fixtures, dots on the tissue itself, and dots in pins that have been inserted into the tissue. So we have a variety of different adhesive strengths to work with, and it's really just going to be kind of a situational thing and determining what's the best way forward in each case. We were able to take the point components you see highlighted in the various colors in the video and align them to CT scan meshes for visualization and coordinate system alignment. And if you look at the bottom of the video, you'll notice that point component in pink, that is what we were using as reference for the rigid body motion compensation. And Justin spoke to this a little bit, but the takeaway is that rigid body motion compensation is going to let us measure the spine movement against, in this case, L5, instead of against the load frame or the camera system. And this is going to be a great way to for us to be able to neglect any disturbances that might occur due to floor vibrations or things of that nature. And our goal for this analysis is going to be to plot displacement versus time at each point, And to determine the intervertebral distances, we're going to be particularly interested in what's happening in the distance between LV4 and LV5. And so with that, let's go ahead and switch over into the project. And so this is what the Go and Correlate Professional software looks like to the user. You can see here the main window is going to be the image view of our measurement. I can go ahead and switch back and forth between the left and the right cameras if I need to. And the images are all going to be organized in our timeline here at the bottom. And so as I click through and scroll, you can see that we're tracking each of these point components at the different vertebrae. So over here in the left side of my screen, this is the Element Explorer. This is where I'm going to have my components of interest stored, and as well as these surface inspections. We're going to open up the surface inspections and look at our displacement field fairly shortly. But before we do that, I just want to call out the CT meshes that we were able to get. And so you see that we have these translucent constructions up here on the image. These are now aligned to the dots that we've placed directly on the specimen and on the fixture. And now I can go into a 3D view. And as I click through, we're able to see how we're able to see those meshes as they displace, assuming rigid body. And so to start digging in and start investigating our displacements, we can look in our inspection category under our vector fields. And then if we make these visible, we'll be able to see, you notice that I've got a color scale pop up on the right side of my screen. And as I click through, we're able to see for each image the magnitude and direction of the displacement vectors. So this is pretty powerful, and it really is as easy as that. Some people might be wondering whether we'd be able to break this down further by direction, and we absolutely can. And so our coordinate system here is aligned with the LV5, lumbar vertebra 5, and if we activate the visibility on it, this is what we're looking at, Z positive vertically, Y positive towards the camera system, and X positive to the left horizontally. And so now what I can do is I can select my point components, inspect with keystroke. I can pull up, I can check out the displacement. That's going to be the vectors that we were seeing previously. But I can also look at, say, if I wanted to just have the displacement in the vertical direction, I am more than able to. And now, of course, I would need to change my scaling here, but hopefully you can see that, that now we are purely isolated to that vertical direction, which is great to see. And one thing I wanted to point out, I mentioned rigid body motion compensation earlier. And so notice that I have full control over what rigid body I'm using, or what component I'm using for my rigid body motion compensation. And if I go ahead and turn on these vectors, then we notice that towards the bottom of the specimen on that LV5, the displacement there is 0. And so if we wanted to say, that we don't want to account for the common movement of LV5, then we can just turn this off, recalculate, and then again, we're able to see our scaling remains constant, but we can see how much it's changing when we're taking into account all that motion. So when I'm taking a project, I'm always thinking, what am I using as my reference here? What are the displacements that really matter to me to be able to see? Jumping forward a little bit, we can also study rotations in a very quick way. And the easiest way to get that done is to create local coordinate systems. And so here we have activated visibility on coordinate systems that are tagged to the fixture or in one case for LV3 directly on the specimen. And as I click through, we can see those coordinate systems as they translate and rotate over the course of the test. And so things that we would want to see, things that we would want to really analyze in this way would be the rotation. So we can go ahead and make those visible. And so now, if you notice, I've got labels popping up for each of the coordinate systems showing me the rotation in X at each stage. And even better, this data is automatically captured in my diagram. And so I can very quickly and easily see the values of those rotations. And of course, as we would expect, since we are holding LV5 as our fixed reference point, we see that angle is 0. And as we move further and further up the spine, the angular displacements are becoming greater. And so the primary motivation for bringing in the nice CT meshes that we had here was to be able to find the intervertebral distances. And so if we go ahead and take a look at that, what we've done is, based on the knowledge of where LV2 and LV1 are, we are able to create a surface. You can see the colored region here, and using this, we're able to find the distance from LV2 up to LV1. And so as we're looking at this region on LV2, we can click through. And then based on the software's understanding of the geometry gathered from the CT and how that geometry is moving based on being tagged to the point components, we're able to generate this full field map. And then we can very easily come in and highlight points of interest. It looks like I might have a maximum distance in this region. So I can create that point inspection, open up my diagram, do a quick recalculation, and I'm able to track that distance as it's changing. And so these would just be kind of your first steps in performing this analysis, creating the point components, inspecting them, and any other various inspections of interest that we might have. And then so once we have this data, we can very easily share it in any way that's convenient for us. The quick way is I can click this floppy disk here, export diagram contents, and then I'm able to spit out a CSV that will contain all of the information that I have indexed over time in this plot. Another quick way to share data, especially kind of the qualitative full field data, is to create report pages. And so this is a great way to highlight the very important things and just kind of the meat of the measurement. And then once we have these, we're able to export them as either images or PDFs or videos, just so we can really take a look and share that data quickly in a great way. And so if I want to get an idea of some of the displacements happening on the point components, remember we had just the magnitude of the vectors. Select these. We have the magnitudes of these vectors. I'm going to switch my rigid body motion compensation back to LV5. And then, again, it's really just as easy to isolate any single point of interest by just calling out these points individually. and I have a full-time history of this data. Another thing I'd like to point out is that we aren't only limited to CT meshes as far as external inputs. What we could also do is from this load frame, feed the load out in pounds or newtons or kips or whatever unit we're using. We can feed that load out into one of our controllers and use that to produce additional correlation studies. And so looks like I'm about running out here, but I just wanted to give you a first steps view into the software, into what we can accomplish with it, and just how quick and easy it is to create these inspections and measurements.
Excellent. Thanks so much, Andy.
Absolutely, it's my pleasure.
Great. We did have a few questions come in over the course of the review there. Okay. One, I think, was sort of answered as you were going through there, but it does beg another question, so go ahead and ask it. What's the purpose of inputting the mesh in the software, feeding that CT scan? You could get the displacement vectors from the rigid bodies in the video. What application for the meshes do you see with the software? So you showed the distance mapping there between the vertebrae, but why else would you want to import a CAD model or a scan or anything along those lines?
Yeah, so there's plenty of great reasons for you to be able to do that. Obviously, the biggest one in this case, we're able to do that distance mapping in a really quick way. But another reason that we would want to do it is if our coordinate system, by default, our coordinate system is just in camera coordinates. So that's where the origin is in the center of the image with Z positive towards the cameras and Y positive vertically. And as we saw in this project file, that's not necessarily going to be the appropriate reference frame. So we wanted to make sure we were aligned with LV5 in the coordinates that would make sense for the user. And so if we have external data, whether that's a CT scan or even a CAD file that we have in coordinates that are already sensible to the design team and to the test team, then that alignment is going to be critical to have.
Excellent. Okay. Did have another question that came in. I'm trying my best to ask this. Can you shift where the location of each vertebrae coordinate frame, that is, move each to the center of the vertebrae of the top of each disc? I hope I asked that correctly. Can you understand the question, Andy?
Yeah, no, I get it. And yeah, this is a great point. So just like we can move our global coordinate system, our overall coordinates, we can take those small local coordinate systems, and then we also have a lot of flexibility in defining those as well. So we're able to change them based on geometry. We can go in and manually input, like, hey, I want this to have a 5 millimeter offset from where I originally created this. And so there's a ton of ways to do that in the software.
Great. So we have another question here from Robert DuRocher. Was the FSU including the ligaments? If yes, are strain measurements possible?
I have to apologize. I'm not familiar with the terminology there. The FSU, including the ligament. But I guess I would say, if I were to just kind of answer this a little bit more, the spine unit including the ligament. Oh, I see. Thank you. In this case, we would want to go ahead and pattern it up. As I said before, I have had experience on a very similar project to the one we just reviewed, where we did go ahead and apply with paint that black and white TV style pattern. And then so when we do that, The full field strain measurements are absolutely possible, but in this case, we would need to do a quick redesign of our specimen here.
Excellent. All right, well, thank you very much, Andy. I think we're out of questions at this point. If any of the attendees from today have any further questions, you're certainly welcome to touch base with us and follow up, ask questions that you have. We'll be sending out a follow-up message to thank you for watching, and including a recording of today's webinar as well, so that you can review or share with colleagues. If you do have any questions, feel free to respond there, and we will be certain to get back in touch with you. But otherwise, thank you so much for your time today. We hope you learned something that's useful to you, and we look forward to supporting you in the future. Thanks again, and have a great day.